Morning, Marissa.
Good morning. How are you?
I'm good. How you doing?
I'm well. I'm just received some candles in the mail, and every single one of them is shattered, so I'm cleaning up that mess.
Candles?
Yeah, Bath
Uh,
and Body Works was having a sale. I was real excited about it, but the UPS driver didn't agree with me.
oh, that is sad. Hello, Sindus.
Good morning.
How you doing?
I'm doing good, just waking up.
I think you're doing better than Marissa. She just lost a bunch of candles.
Oh no, that happens to me a lot with Bath and Body Works. Whenever the UPS
Mm.
drivers just drop off the stuff, they just slam the box on the ground.
Yeah, they literally drop it off, don't they?
Yeah, and the good thing is you can call and then they resend the candles. But it's also the packaging that Bath and Body Works does. Sometimes they're like really lazy.
mm.
I agree with that, and it's funny that you mentioned the UPS driver specifically because I actually have the Nest camera system, and I saw when he dropped off the package, and I heard them break, and he kept going.
Mm. Now, he didn't just pick it up and then drop it again, right?
No, no. I mean, at that point, might as well, though.
He'd be a FedEx worker.
Yeah. All right. Let me see.
Well, don't whine. You have
I think that's Amber. Hello, Amber. Hi, Ronald. Morning, Jillian, Ariana, Gabriella.
Morning.
Good morning.
Good morning.
Morning, Alyssa.
Good morning. I had a quick question about the honor lock practice. When is that due? Because we need a password to get into it.
You shouldn't need a password. If you're using it, if you're needing a password, it means you're in the wrong browser.
Okay.
You need to do it in Chrome. Are you in Chrome doing it?
No, but I can like log out and then do it in Chrome.
Yeah, do it in Chrome. And now it's not due per se.
Okay.
The idea is it's just for you to practice on, and it's fantastic that you tried it because now you realize you need Chrome.
Okay, thank you.
All right. Berkeley's here too. Hi, Berkeley.
Hi.
And Nilafar. Hi, Nilafar. And we got Jack. Hi, Jack. And Tony. Morning, guys. And we got Leah. And we got Corey. Hi, ladies.
Good morning.
And Kyle. Morning, Kyle.
Good morning.
Okay, well, good morning to anybody I didn't say good morning to. It's now 8 a.m. We'll go ahead and get started. All right, so I will go ahead and share the screen here. All right, we are going to start by going over, at least briefly, I'll go over the kinetics, and then I want to spend as much time as I can on the actual problems, but I do want to give a little background first, make sure you all understand at least the basics of the kinetics problem that we're going to be talking about today. All right, so we're going to start out here. We've got reaction orders and rate equations. So let's talk about what a rate equation is. So this is a chemical reaction. You can see it there, 2HgCl2 plus C2O42 minus, and that gives all these different products. Now, it turns out that the rate equation for this is rate equals K times, now those square brackets mean concentration. So that's what you're going to see routinely. Anytime anything's in square brackets, it means we're talking about concentration. You can see the HgCl2 is effectively to the power of 1, and the C2O42 minus is effectively to the power of 2. And you can see that there. Those are called reaction orders, those powers. And we're going to be focusing on how to calculate those powers. We're also going to talk about what those powers mean and how you can apply them to other things. So rate, what does rate mean? Well, it just means speed. It means how fast the reaction's going. That K there is a rate constant, and that is going to be, as the name suggests, a constant value, but only at a given temperature. I think one thing that you all are probably aware of is that as you heat a reaction, it goes faster, right? That makes sense, right? So, you know, that K will increase as temperature increases. But at a constant temperature, K remains constant as well. So rate. So rate is equal to K, which is the rate constant, and that's multiplied by the concentrations of these different reactants to those specific powers that I talked about earlier. And it also makes sense that how fast a reaction goes should depend on the concentrations of what you're reacting. I mean, the more you've got of something, probably the faster it's going to react. How much faster is going to depend on these orders here that we talked about, these powers. So I'm going to go into that as well a bit. All right, so rate, another word for speed, how fast the reaction's going. You know, chemists always have a vested interest in making reactions go faster. So that's the basics behind all this. Why we're even interested in the first place. You know, you don't want a process that you're trying to get going to take, you know, years to go. I mean, that's not very efficient, and it's not going to make you a lot of money either. So, you know, you got to make sure that your reaction's going fast enough, and we can do things to tweak that by using these rate equations that I'm talking about here. Now, the other thing I want to talk about with the rate equation is that there's no linkage necessarily to the coefficients that you see here. See the 2 here? There's not a 2 up here in the order. This one has like a 1 in front of it, but this is a 2. So there's no real link between the orders and the actual coefficients you see here. Now, it turns out often, well, probably at least 50% of the time, you will find that the orders and the coefficients are the same, but they don't have to be. All right. So the orders, yeah, we talked about that. So what do they mean? Okay, so the orders, how do they help you? Well, the bigger the order, the more effect that specific reactant will have on the rate. I think that makes sense, and I'll tell you why. If you've got a rate equation, and this is the one we're talking about here, and let's say we start out with a concentration of 1 molar on both reactants, and I just go ahead and substitute in that 1 for these concentrations. That's all I've done here, just taken the 1 and put it into the rate equation right here. Then what we're doing is just plugging all that in. You can see the rate is just going to be straight K. Now, if I double the HgCl2 and leave the C2O42 minus the same, you can see the rate will end up being 2K. But if I double the C2O42 minus and leave the HgCl2 as it is, as 1, you can see the rate is going to be 4K. Now, what you're seeing here is that by doubling the second reactant, because you've got the square here, it has a much bigger effect on the rate. That's all I'm trying to get at. That's how the rate equation helps you. You can say, well, I want to speed up this reaction. What will have the biggest effect? Well, changing this one will, because it's got the square on it. That's all I'm saying. That's all I'm saying. Does anybody have any questions so far? Okay. So this is the kind of setup that we're going to be using here. Now, you're actually going to be doing this in the lab as well. You know, this very same thing. And what you're given is a table, and this table will actually allow us to determine those reaction orders. Now, I know I've already given you what the reaction orders are for this specific reaction, but now I'm going to show you how it would actually be calculated. So if you take a look at the setup here, we've got 4 different experiments. And look closely at what we've done here. Let me see, I'll see if I can, I don't want to do it from current slide, all right. Okay. I won't always have it full screen because I need the whiteboard as well. But look at the actual concentrations here that we're dealing with. So we start out with 0.105 and 0.150 of the HgCl2 and C2O42 minus respectively. Now look what we do in the second experiment. We keep the HgCl2 the same, but look what we did to the C2O42 minus. It's now 0.300. We doubled it. look over here. These are the rates, the initial rates. I'll explain what those are in a second and where we get those from. But I mean, they're always given to you, but I'll show you what their origin is in a second. But if you look closely at it, you can see what's happened to the rate. You see the rate has clearly gone up because the concentration of C2042 minus has gone up. Now looking down here, you can see we've got this one, 3. We can leave the 0.300 the same, but this one is now halved, and we can see what effect that has on the rate as well. Okay, so I'm going to go through this and show you exactly what we're doing with it in a second. Let's talk about the initial rate here. All right, now this looks complicated, but it really isn't. So what are we dealing with? This is a reaction. The reaction specifically is just this C4H9Cl going into products. That's all. That's all it is. Just this reactant going into products. Now, it makes sense that if we start out with 0.1 molar, that the concentration of this reactant is going to go down. Well, it's not really much of a surprise. What's happening to the reactant? Well, it's reacting. It's turning into products. So the concentration is going to go down. Starts at 0.1. So what's this initial rate here? Well, the initial rate is the slope of this line here if it's tangent to the curve. Now, what I mean by that is you've got molarity here, concentration, and here you've got seconds. And this is just the time of reaction going on here. And if you were to find the slope, then we're talking about y over x, which is molar over seconds, molar per second. That is the unit of a rate, the molar used per second, if you will. So the rate is the concentration as this goes down. Now, obviously, the faster it's going down, the more this will slope, the bigger the rate. And that's what we're talking about. So that gives you a little context as to what this column is showing. Now that can be molar per second, molar per minute, molar per anything, any time unit you wish under the sun, but it's always going to be molar per something. Does anybody have any questions so far? All right, just to clarify what I'm trying to do here is I'm trying to show you how we can use this data to come up with this rate equation here that shows the orders as being, I wish you'd go away. Hang on, I don't know why, here we go. To come with the 1 here and the 2 here. That's what we're trying to do. Now, I know I've already given it to you, but I'm just showing you how we come up with it. The only way we come up with it is by doing experiments and figuring out what the initial rates are. So you might be wondering, well, how would we determine these concentrations? Well, you know, there's lots of different things you can do. If your reactant, for example, is colored, then maybe the lightening of that color might be an indication of the concentration. So there are things we can do, spectrometers we can use, equipment we can use to measure the intensity of color. In the reaction you actually do in the lab, you start out with something yellow that turns into something colorless. And that's your indication of a change in concentration going on in the reactants. But you know, you'll do much more with that when you get into the lab. So that's in a couple of weeks, you'll start that lab. Okay, does anybody have any questions so far? Okay, so how do we use this data to our advantage? Sorry, was that a question? No. So how do we use this data to our advantage? Well, what it's all about is comparing experiments. So comparing by putting one over the other. So what do we choose? Well, here's the idea. If I want to find M here, let's look at the rate equation up there, and you see what we're looking for is M and N. I won't point to it because it's going to bring up that other thing that I don't want to bring up. But you look at the very top there, you'll see the rate equation. Rate equals K, HgCl2 to the power of M, C2042 minus to the power of N. We are looking for M and N specifically, those powers. And we can do that by comparing experiments. But what experiments do we compare? Well, if we're looking for M, what we're going to do is try and find experiments where the C2042 minus is going to be the same, so that when we put one experiment over the other, and I'm going to show you how to do that in a second, one experiment over the other, then the C2042 minus will cancel. So under what circumstances will that happen? Well, if we use 2 and 3, you can see the C2042 minus is the same, so that's going to cancel. If we used 1 and 4, that would also cancel as well. So that's how we choose. That's how we choose what reactions we're going to use in order to find a specific order. So in this case, we're looking for M, which means we need everything else in the equation to cancel. All right, so let me get my whiteboard out here. And I'll explain this a little bit more because this is kind of the whole point of what we're doing. Oops, I don't want to move this. This is not being very cooperative. Here we go. Okay. And I want to make sure I've got the chat box up here as well. Because I don't want to miss any questions. There we go. All right. If anything pops up in the chat box, please let me know and I'll answer it if I miss it. Sometimes I'm not concentrating on what's going on in the chat box. Okay. All right. So as I said, if we want M, then we're going to compare experiments 2 and experiment 3, and we've got these rate equations here. Now, you're always given the rate equation, and you can see it here. Rate equals K. You'd be given this in any question. HGCl2 to the M, C2042 minus to the N. Sorry about that. I'll go off the screen here because I've got a writing pad that I'm using. I'm sorry about that. I will try and stay more on the screen here. There we go, that's better. All right, so we've got our rate equation here. We're comparing rate 2 and rate 3. So hopefully I don't drop my writing pad here. All right, okay. So rate 2, in this case, over rate 3 is what we're doing. And it's K times the HGCl2 to the M. And enlarge this a little bit. And C2042 minus to the N. And then I'll put little 2's down here as well. And it will do the same thing for 3. Now the 2 and the 3 here are simply the experiments. So you got experiment 2 and experiment 3. So the concentrations in those specific experiments. Now the rates are the initial rates that you're given here. So I'm going to go ahead and plug those in. So we've got 7.2 times 10, 7.20 times 10 to the negative 5. Now it's molar per minute over 3.60 times 10 to the negative 5 molar per minute. So you see the units are going to cancel here. We're comparing the two. Of course, the K's will cancel as well. Look at that. They're gone. And then you've got your 0.105 molar, and that's all to the M, over 0.052 molar, and that's all to the N. The M, sorry, as well. Now the other stuff is going to be the same. So sorry about that. But this is going to cancel anyway because they're the same. So they're gone. And all we're left with is what I've got on the next slide, which is 2.00 equals 2.02 to the power of m. So look at what we did there. We deliberately chose a certain set of reactions. We chose, where are we? Back over here. We chose reactions 2 and 3 because these are the same. We want to find out the order with respect to this guy here, HgCl2. So we choose reactions where the C2O42 minus is the same. So you'll notice there that and you know, just in very short term, I can tell you this, that the reaction rate seems to halve when we halve the concentration. Isn't that interesting? So you've got 7.20 going down to 3.60 if we ignore the 10 to the negative 5. That's going to be half, right? Look what happens here. The concentration was 0.105. You halve that, it also halves the rate. Now that allows us to determine what m is, and you know, m is always a whole number as well, so m is going to equal 1 here. All right, does anybody have any questions? Any questions at all? Now, I'm using rate 2 and 3, and that's all well and good. I could have used rate 1 and 4, but you'll notice I did rate 2 over rate 3. I could have also done rate 3 over rate 2. There's nothing to stop me doing that, nothing at all. However, I always like to arrange it so that the biggest rate is on top. That's why I chose rate 2 over rate 3. So that I end up getting whole numbers rather than fractions, because that's what's going to happen. It'll still work if I do it the other way, but it's going to be a lot harder to figure out what's going on, I think, if you do it the other way around. But that's the upshot of it. Does anybody have any questions? So that gives me m. If I want n, then I'm going to have to find two reactions where the HgCl2 is the same. So 1 and 2 is going to be okay, and 3 and 4 are going to be okay. Now, I can't remember what I used here. I think I used 1 and 2. Oops. And you see, I'll use 1 and 2, but I've done rate 2 over rate 1. Let's go back and see why I've done that. So you got rate 2 here, 7.20, and then you got rate 1, which is 1.80. So I've done 2 over 1. Now you'll notice what that's going to do is going to cancel the HgCl2s because they're the same. And then we've got the C2O42 minus. Those two are different. So that's how I've got it set up here. So I've got, I plug in everything like I did previously over here. You know, all of the different rates, and the concentrations. These guys cancel, the K's cancel, as I said earlier. And you'll see it becomes 4 equals 2 to the power of n, so n is equal to 2. So that's going to be the order with respect to C2O42 minus. I mean, if you look at it, you'll see that by halving the concentration of C2O42 minus, it means that we have 1/4 or fourth, you know, it's 1/4 of what it used to be. So that's the relationship that we're dealing with there. Does anybody have any questions? Anything at all? All right, let me say a little bit about solving for a power here. Because what we're doing here is if it's always going to be, whoops, sorry about that. It's always going to be something of this setup here. And what we're doing is we're solving for Z effectively. It's a power. Now, solving for a power is not that easy, generally speaking. Let me give you an example. Let's say we have 8 equals 2 to the power of n. Anybody want to tell me what n is?
3.
3 is correct. Some people might have looked at it and said 4. But that's not the game we're playing. It's not a multiplication here, it's a power. So it's 2 multiplied by itself that number of times. It becomes a little bit more difficult though, doesn't it, if we've got bigger numbers. Let's say we've got 64 equals 2 to the n. That's a bit harder, isn't it? So, anybody know what n is? What's that?
6.
6? I don't think it's 6. Is it? Let's have a look. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, and yes, it's 6. You were right. Thank you. So n is equal to 6. That's right. So, you know, that's one way of doing it. We can do it by trial and error. There is another way. So what we can do is we can do this funky thing. I'm going to clear all this out here. And we're dealing with, again, x equals y to the z, solving for z. And what we can do is we can take the log of both sides here. So log x equals log y to the power of z. And then using some great log math here, we can do this. Log x equals z log y. And z equals log x over log y. So that's another way of doing it. You can actually solve for z using logs, which is pretty cool. So you're at liberty to do that too. But the thing is, you're always hoping z is going to be, if not a whole number, then bloody close to 1, right? You really want it to be close to a whole number. But you will always round it to a whole number in any case, even if it's not a whole number. I mean, clearly in this example here, I mean, if you were to solve for m straight, it wouldn't give you a whole number, but it'd be close to 1. I can guarantee you that. And then you'd round it to 1. You always take the nearest whole number. All right, does anybody have any questions? Any questions at all about finding these reaction orders? That's all we've got. That's all we've done so far, is found reaction orders. Any questions? You're either all understanding or you're all completely lost. I'm not sure which, but I'm hopeful it's the former rather than the latter.
It makes sense to me.
Okay, thanks, Reese. All right, let's see what we're doing. We're going to, well, the overall order. The overall order represents the sum of the orders. So in this case, it's going to be 1 plus 2 equals 3. Now, I'll tell you more about the significance of that in a little while. It's we call that molecularity, that 3 there. And what it gives you an indication of is how many molecules are involved in the slow step of this reaction. And I will elaborate on that in great detail later on. But yes, there is significance to this adding of the 2 orders together. So now that we've got those orders, we can find our friend K. So how do we do that? Well, we've got all the information we need. So if we want to find K, now remember what I said about K. I said K was a constant value, which means that it doesn't matter which experiment we use, we're going to pretty much find the same value of K for any experiment we choose here. So what are we doing here? Well, let's have a look. So rate 1, I'll do it over here on the whiteboard, sort of lay it all out for you. It's going to be pretty much what I've written here, but I'm hoping that by writing it out, you'll see it a little bit more clearly. So rate 1 is equal to K, and we've got HgCl2 1. Remember, that's experiment 1 to the power of m, C2042 minus 1, and that's to the power of n. And now this is all of this here is going to be from this first experiment. I'm going to plug in all that data So everything I'm getting here comes from experiment 1. This concentration, and the initial rate, HgCl2, C2O42 minus, and the initial rate. Okay. So the initial rate here, 1.80 times 10 to the negative 5. And the unit on that was molar per minute, which I get off the table. Now we're looking for K, that's our friend, that's who we're looking for. And then we've got our concentrations, 0.105. Remember, this was just off the table as well. No magic here. That's to the power of 1 times, and we've got 0.150 molar, and that's to the power of 2. So the 1 and the 2 here come from these values, the M and the N, that we just calculated earlier. So I'm just plugging those values in. Now, getting the numerical value for K is not very difficult. What we come out with here is K equals 7.62 times 10 to the negative 3. And the unit here is m to the negative 2 minutes to the minus 1. I'll explain how I get that in a second. But let's first of all concentrate on the numerical part of this. Is anybody uncertain about how they might do that? I'll tell you what, hopefully you've all got a calculator in front of you. See if you can solve for just the numerical value of K. I'll wait. I'll give you 30 seconds or so to make sure you are getting that value. I want to make sure you're getting 7.62 times 10 to the negative 3.
Should we type it in the chat if we have it?
Oh, not necessarily. Actually, I'd rather know if you don't have it.
Okay.
Yeah, so if anybody's not getting that, I'd like to know so that I can help remedy the situation, if I may. Like in the calculator, this is what I would do. I'd do 1.80, then I'd do EE negative 5. So I definitely use this EE button. Is everybody familiar with their exponent button on the calculator? Anybody have any questions about how to find that? Okay. And then that would be divided by 0.105. Whoops, 0.105. And then what I would do is it's divided by, and I put this in parentheses, 0.1. You probably don't have to, but I'll do it anyway. And that should give you the right answer. That's probably how I'd do it. Does anybody have any questions about getting the numerical value, 7.62 times 10 to the negative 3? I usually have at least a couple of people who have trouble doing it, and that's okay, because we get to fix that problem now, so you never have it again.
If you want that equation to work on the calculator, you got to put brackets over the 0 and the second bracket over the squared.
It depends on your calculator. I mean, another way of doing it, you could do divided by 0.150 without the brackets here, and divided by 0.150. That's pretty tricky, isn't it? So anything that you're dividing, anything that goes on the bottom, you can divide by. And this is how you can just plug it into your calculator. That'll work as well. All right, does anybody have any other questions about just getting the numerical value? All right, but little k also has units, so I want to show you how we get that as well. Get rid of that. Okay. So I've got this business here, m to the negative 2 minutes to the minus 1. Ooh, gosh, that seems a bit nasty, doesn't it? Where does that come from? Well, let's just ignore the numbers here, and let's just focus on the units. So we've got K is equal to, now it's going to be molar per minute divided by molar times molar squared. All right, so that's how that's what we're doing so far. Now, what did I do there? I just took the units. And how do I manage that? Well, there's a unit there. That's the molar per minute that goes on top. And that's divided by molar to the 1 and molar to the 2. All right, does anybody have any questions? Now, there's a couple of relationships we can use here. Reese, I'm going to ask you to mute if you don't mind. I think yeah, thank you. There's a couple of relationships that I want you to be aware of here. So let's say you've got a to the, actually I'll do it again. So a to the x times a to the y. That equals a to the x plus y. A to the x over a to the y equals a to the x minus y. I'm sure you're all aware of those two relationships for powers. When you multiply, you add the power. When you divide, you subtract the powers if it's the same base. And that's what we're dealing with here. So on the bottom, you can say, well, that's equal to K equals molar per minute over m to the power of 3. Everybody with me on this? Anybody have any questions? And then we can say that that equals m to the negative 2, and we'll say minutes to the minus 1. Now, where did the minus 2 come in? Well, that's 1 minus 3 is negative 2. That's where I'm getting that from. And the minutes to the minus 1 is because it was slash minute or per minute. Generally speaking, when we're dealing with these kinds of units, we either keep it as all numbers or we can use slashes as the negatives, but generally we don't mix those two. So that's why I put it m to the negative 2 minutes to the minus 1. So that's how we're getting the unit on little k there. Does anybody have any questions? So you're all hunky-dory with that, hey? Nobody has any questions about getting that unit? Now, I want to point out that unit's going to vary depending upon the orders. Right? So it's not always going to be that. You know, depending on what your M and N are, that's going to determine your K or your K units. Yeah, that's a bit nasty, isn't it? All right, anybody got any questions? Seriously, any questions?
I have a quick question.
Yes, Gabriella.
So I understand how you have m to the third at the bottom there, but can you just explain again how you, when you put it after the equal sign, how you have m to the negative 2 with the minutes to the negative 1, how you got that step again?
Okay, so you can see here, a to the x over a to the y is equal to a to the x minus y. Now in this case, x is like 1 and the y is like 3. So 1 minus 3 is negative 2.
I see.
All right, now the minute to the negative 1 is the slash minute, which is the same thing.
Okay.
Is that all right?
Yes, I got it now. Thank you.
All right, any other questions?
Why did you choose to put the molar over minute over the molar times 3?
Could you repeat that, please? I'm sorry.
Why did you choose to do it in like the division way compared to the multiplication way?
Because this is division here, m over m cubed.
But isn't it in the multiplication setup above? I guess not.
Well, no, you see, what I did was, the multiplication setup I used down here. This is 1 plus 2 is 3.
Oh, okay.
All right, so I used that on the bottom. But when I had to divide these, then I had to use the division setup.
Okay, sounds good.
Okay.
I have a question.
Yes, Iris.
1.80 times x to the negative 5. For finding that value, could you go through how I should punch that in again? Because it's not working for me.
You mean into your calculator?
Yeah.
Yeah, okay. So you should have on your calculator an EE or an exponent button. What kind of calculator you got, Reese?
I have a couple different ones. Right now I'm using the TI-30X2S.
Okay, that's not my fave. It's hard to,
But I also have a 30XA.
I love the 30XA. That's my
Okay.
favorite. That's my favorite calculator in the entire world.
Okay, then I'll use
You know, if this was a girl, I'd marry it.
that.
I'm serious. I'm serious. That's my favorite calculator in the world. So if you look at that, you see the EE button? It's down.
Yes.
Okay. So what you would do is you do 1.80 EE negative 5.
Got it.
That's how you plug it in.
Okay.
1.80 E negative 5. You don't put a 10 or anything else in there, but that's how you plug it in. If you'd like, you know, you can show it on the screen too, Reese, if you're comfortable turning on your video. That's up to you.
Showing what?
I'm sorry?
Showing what? The calculator?
If you're having trouble plugging it in, yes. If not, then
I got that part in.
Okay, all right.
The only part that I've got confused with is the part where we're doing like the 0.105 molar after this part.
Okay. So you would just do divided by 0.105 and then divided by the 0.150 squared, but you could put that in parentheses in your calculator.
Okay.
That might be what you're having trouble with, I guess. The square part.
Maybe.
Now, the other thing you could do, I mean, it's a kind of a last resort, is you could just do 0.150 squared and write down what that value is. And then if you did 1.80 divided by 0.105 and then divide that again by whatever you got on the squared here, that would give you the right answer as well. But really, you should be able to put it in your calculator as one step. It's far more convenient.
Okay. So like after I've calculated the 1.80 times 10 to the negative 5 and I have that number, and like should I just hit 1.80 EE negative 5 and then hit equals, or just do divide straight from there?
Just use you just do divide straight from there. So then you do divide 0.105.
Okay.
I'll just write down exactly what you need to plug in. So EE negative 5 and then divided by 0.105. And then do divided by and then do a parenthesis, 0.150, and then hit the squared button and then close the parenthesis. And then hit equals. And that should work out for you. Do you see the X squared button on
Yes,
your
it did.
Yep.
Yes, it did.
Okay,
That
good.
worked.
Good, good. All right, excellent. Anybody else have any questions about this? Okay, let's go take a look at the test question, and then I'll show you the questions as they relate to that on the test you'll be taking. Okay, so let's take a squiz. So test 1. Reese, I'm going to ask you to mute again, please, if you don't mind. Okay. So I'm just going to pick one of these at random. So this is a pen and paper test that I give my students, generally speaking. You're going to take something a little bit different. I'm going to show you the relationship of it, though. So you've got the experiments here. You can see you've got the concentrations, you've got the rates, and what we're interested in are the orders of A and B. So M, N, our friend K, and the overall order. That's what we're looking for. And we're going to do those calculations exactly the way that I showed you. So I'm just going to briefly, whoops, I didn't mean to do that. I did not mean to do that. That is annoying. Sorry about that. Not the first time I've done that either. All right, where are we? 2046. Go back to where we were. I'm going to show you how that works out. Okay. So you can see what the students done here is they've done here. We wanted to find the M value, which is the one with respect to A. So the student used experiment 2 and experiment 1. And they did experiment 2 over experiment 1 because experiment 2 had the bigger rate. Is everybody okay with that? Does anybody have any questions? So what they came out with was 26.15 is equal to 5.00 to the M. 26, though, is pretty close to 25, so I'm hoping you can see how M would be 2. You could do it, you could just eyeball it, but you can see the student used the log method to figure out the M value there. To get N, we needed to use the experiments 1 and 3 where the A values were the same. And you'll notice we did, well, it doesn't matter which one you do because they're both the same rate. So this student did experiment 3 over experiment 1 and came up with 1.0 equals 6.00 to the N, and N equals 0. Now remember, anything to the power of 0 is 1. That's how you solve that. But if you did the log thing, log of 1 is 0. So that's how we know that N is going to be 0 there as well. Does anybody have any questions so far about getting M and N? Now I'm just going through the whole thing here. Don't fret. This is not what you'll be doing. I'll explain in a second what you'll be doing, all right? But you won't be doing this exactly. I'm just trying to show you how this gets applied here. So we do the same thing here to get K as we did previously. And you can see we're using experiment 1 here. And the student just plugs everything in as experiment 1, 8.62 times 10 to the negative 5. K, 0.200 squared, that's for the M value there, and 0.652 to the 0, which is 1, of course. And then we can solve for K, and K is equal to that. And those are the units there. M to the negative 1, H to the negative 1 are the units on K there. Does anybody have any questions just about the general setup or how any of those things were obtained?
I just get confused again on the how to write it as M to the negative 1 over, or H to the negative 1 for the units.
For the units, okay. Let's go through this on the whiteboard, okay? Okay. So we've got, our situation is this, we've got molar per hour over M squared times M to the 0, effectively. Now that really means M molar per hour over M squared, because 2 plus 0 is 2. Is that okay so far, Alyssa?
It's good so far.
Sorry, Gabriella, I'm sorry, you were asking the question, I apologize.
It's good.
Okay, so 1 minus 2 is negative 1. So that's where the M to the negative 1 comes from. And then we've got per hour here, which is actually hours to the negative 1.
Okay, I see.
You'll notice that 1 over MH is the other way that could be expressed. That's the same thing.
Okay, I got it.
Okay, good. All right, let's take a look. I know you're much more interested in what you'll be doing, right? I mean, I would be. Let's take a squiz. Let's see what you'd be up to. So we've got test 1 here. Oops, ungraded copy of test 1. That's what we're going to be doing. So what you'll notice is that, see this question 1 here, reaction orders M, N, K, overall order. So you've got question 1, question 2, question 3, question 4. All of those have direct relevance to what we just did. It's just that you're kind of doing it step by step in different questions. It's the same thing, I promise. It's the same thing. You're just doing it as separate questions. All right. So what I want to do is go through this and show you exactly what you're going to do for each question. Does anybody have any questions so far? Anybody have any trouble seeing what I'm trying to link here? You're all good? All right. So what we're looking for here in the first one is the order with respect, sorry about that. What happened to it? Don't come back. Thank you. What we're looking for here is the order with respect to A. And then it says round to the nearest whole number, and that's covered there, but you can see that. Okay, so what are we looking for here? So we've got A, we're looking for A. Does anybody want to tell me what experiments we're going to use if we want the order with respect to A? Which experiments must we use?
1 and 2.
1 and 2. So AW, I'm sorry, what's your name? What's your first name?
Alexander.
Alexander. Thank you. I'm sorry. I haven't learned the names yet. So Alexander, why did you choose reactions 1 and 2?
B's the same, so they cancel out.
The same B, right? Yeah, the same concentration of B specifically. All right, so we know we're going to do, in this case, I'm going to do rate 2 over rate 1. Now, you might be wondering, why did I choose rate 2 over rate 1 rather than rate 1 over rate 2? Now, I did that because the 754 is bigger than the 171. That's the reason. So I chose to do rate 2 over rate 1. Now, that's going to equal K, and it's going to be A to the power of M, B to the power of N. And there's that's two's there for experiment 2. And then A to the M, 1, B to the N, 1 on the bottom. So I plugged all that in, and I'm going to get 754. Whoops. And that's molar per hour over 171. Molar per hour. Okay. K's cancel. And then we plug in our A values and we get 0.709. Over 0.119. Now those are both to the power of M. And the other things cancel out, which I'm not even going to show there, but that would be the 0.101 and the 0.101, those are going to cancel. All right, let's see what we get here. I've got my TI-30XA, which I was talking about earlier. Told you I love this calculator. 4.40 is what I get over here. Remember, these units cancel as well. And then we've got 0.709 divided by 0.119. And that's going to be 5.95, and that's to the power of M. I'm going to stop there for a second. Does anybody have any questions about what I've done so far or why I've been doing it? Please, any questions? So remember what I said earlier. I said if you've got x equals y to the z and you're solving for z, then z is going to equal log x over log y. So that means that m here is going to equal log of 4.40 over log of 5.95. All right, so I'm going to go ahead and do that. So log of 4.40. and I get 0.83, and that would round, that rounds to 1. So that would be my M value that I would put into this slot right here. It would be 1. Whoops, 1. Anybody got any questions? Please. That's what we're here for, folks.
I don't have a question on how to do it. I get that. But since for the test we'll be using the honor lock calculator, does the honor lock calculator have log to type it in that way, or?
Well, let's take a squiz. There he is. There's your on-lock calculator.
Okay.
And so to plug that in, let's take a look. I'm going to pull this out over here. Okay, I've got to remember what I was plugging in here. Hang on, let me see. There we go. All right, so yeah, so log of 4.40 over log of 5.95. So that's what you would do. The way you would do it here in the calculator, 4.40 log, I think that's how you do it. There we go. Divided by 5.95 log equals, there you go.
Okay, I see how it is. I just wanted to see that process because I know.
Oh, no worries, no worries. You know, this is what's so valuable about coming to class, because you can ask these questions and we can get these issues sorted right here. It'd probably save you a good 10 minutes trying to sort out, well, how do I plug that in?
Yeah, it does. Thank you.
All right.
I have a question, Professor.
Yes, Kyle, what's up?
Okay, so on the practice assignments, I noticed that it was all multiple choice and they were all whole numbers already. So when it's an open-ended answer like this, we are rounding all the way to the whole number with the order.
Yep.
Okay.
Yeah.
Perfect.
It's because, well, it's all calculated, and I don't know. I'm clever, but I'm not that clever. That's a problem.
Oh, it's okay. I just I figured as much, but
Okay.
I know how these are.
All right, so question 2. Look what we're looking for. We're looking for the order with respect to B. Can anybody tell me which experiments they might compare in order to find our friend the order with respect to B, which would be N in this case?
First and third one.
Yeah, 1 and 3. All right. So more specifically, though, what would you do? Rate 1 over rate 3 or rate 3 over rate 1?
Rate 3 over rate 1.
Yeah. Why'd you choose that? Why rate 3 over? Yeah.
Because the initial rate for rate 3 is bigger than the initial rate for rate 1.
That's right. That's good. So well, I'm going to shortcut this a bit. Whoops. Show you. Once you understand it, I'm not going to show the whole thing here. But let's shortcut this a little bit. So what it becomes is really, if we know that, going back to the rate equation here, rate equals K, A to be M, B to be N, then we know what's going to happen is that it's going to be, well, yeah, rate 3 over rate 1. And we can say that it's going to be 915 over 151 equals, and we know everything else cancels, so it's going to be .615 over 0.154, and those are to the power of n. So it's simple. Once you know what you're doing, it becomes a little bit simpler. And I get 6.05 equals 3 3.99 to be n. So n is going to equal log of 6.05 divided by log of 3.99. And I get 1.30 there, which again would round to 1. The fact they're both 1 is really a coincidence because they're both different problems, of course. Does anybody have any questions about finding m or n in this situation? I want you to remember, this is how your test is going to be, folks. I'm not going to magically change these questions on you. This is how it is. If you can do these, you're good. All right, you're understanding what's going on? You should be fine. Does anybody have any other questions right now? Okay. Take a look at question 3. So we're going to find k. And look what I tell you here. I give you the m and n values in the question. See that? And these guys are going to change. And there's your rate stuff. So this is an experiment here, and I'm asking you to calculate just the numerical value of k without the units. All right, so let's see how we might do that for this one. Not too difficult. So I've got in the question there, rate equals k, a to the m, b to the n. And then I plug in my values, and I get 118. And I'm not interested in units right now. I'm not interested in units, so I'm not going to worry about it. So k, 0.226 to the power of 0 times 0.277 to the power of 1. Now remember where I got the m and n from. I was told them. Right? Now I can solve for my friend k. Now I'm only interested in the numerical value right now. Don't worry about units. Divided by 118 divided by 0.277. That becomes pretty easy, doesn't it? And the answer there would be 426. So as far as sig figs go, we've got 3 sig figs on everything, so the answer comes out to be 3 sig figs as well. That's why I said that. So that would be the numerical answer that goes in there. It would be 426. You'll notice it says, please do not include units, right? Does anybody have any questions just about the numerical value or getting the numerical value?
When you're typing it into the calculator, do you multiply first and then divide by 118?
Actually, the way I put that in was like this. I did 118 divided by 0.277. That's all I did, because I knew that 0.226 to the 0 was 1. But let's say that wasn't 1, then the way I would have done it would have been, if that wasn't, you know, to the power of 0, let's just pretend here, I would have done this.
So just divide the whole thing.
Yeah, you see, that's you know, if you're trying to isolate something and you're trying to take something over the other side, you can just divide by both.
Yeah.
You know, in series like that. That's allowed. Yeah, that works.
Thank you.
All right. Any other questions? Just about the numerical value here, folks. Numerical value only right now. That's what I'm asking about. All right, all right. Let's say I had wanted to figure out the unit on this, just out of curiosity. Let's see how we would do that.
Wouldn't that just be negative the time one by the -1?
Well, let's see in a second. We'll see in a second. So it'd be m to the 0 times m to the 1. Yeah, that's exactly how it's going to go down. So the K unit here is going to be molar per hour divided by m, because that's going to be 1 there. That's going to cancel, and we're left with per hour, which is equal to hours to the minus 1. That's how that unit would come out. Now, remember, you're not asked for the unit here. So I'm just saying if you were, that's how you come out with it. Does anybody have any questions? Any questions? All right, so that's a slash, by the way. Right. Okay. Well, nobody's saying anything, so I'm going to have to assume that you all understand. Okay, fair enough. Let's take a look at the last one here. A value of K is found from this rate equation. If m equals 3 and n equals 4, and the unit for rate is molar per hour, the unit of K is found to be m to the x, h to the negative 1. What is the value of x? Ooh, now this is where we get into the unit. Let's take a squiz. All right, so per the question, sorry about that. I keep on doing that. Okay, rate equals K, A to the M, B to the N, M equals 3, N equals 4. Now, I know that because I'm told that. See that? M equals 3, N equals 4. All right, let's go back to our question here. So the rate is molar per hour. That's what we're told in the question as well. And the units would be K, M to the 3, M to the 4. You're with me so far. Does anybody have any questions? We're just looking at units. We're only interested in units. All right, so K equals, I won't shorten this out yet. I'll do molar per hour over M to the 3 times M to the 4. Is everybody okay so far? Does anybody have any questions? No tricks here, folks, no tricks. Okay. Molar per hour over M to the 7. And then equals M to the negative 6, H to the negative 1. So what's the value of X? X is equal to minus 6. And that would be the answer I'd plug in there, minus 6. All right, take a look. Make sure you understand. Any questions?
How did you get H to the negative 1?
Okay, do you see how it's molar per hour and you've got a slash H here? Slash H is like per hour, so it's hours to the minus 1. It's like 1 over H.
Gotcha.
All right.
So since it's negative 6, it just is negative 6 because the hour per second is just H1.
Yeah, you're only after the value of X. If you look at M to the X, H to the negative 1, we're only looking for the X, which is negative 6. Is that all right? Again, no tricks. I'm not trying to be tricky here. Does anybody have any questions about that? A lot of the time, people get this wrong, but it's one of those things. You know what you're going to get. You know what kind of question you're going to see. And once you know how to do it, it's easy, right? That's what I'm hoping. No tricks. It's all transparent. Any questions? So remember with this test here, that it does show you the answers when you submit. So you go down the bottom, you submit. And the thing is, you don't have to do the whole thing. You can just do questions and submit. Right? So you want to do those parts. You want to do that question, you submit it. Oh, it's only answer 3 questions. So what? So now I'll do that. Submit it. Ah, and look here. It'll tell me my answers. Oh, that's unfortunate. I got question 2 wrong. Wonder how that is. Okay. Whoa. It's embarrassing. I wonder what I did wrong there.
Maybe you didn't type it in.
Maybe I didn't type it in. Maybe I didn't.
I was gonna say, I think you got it right. You just typed it in wrong. Yes, I wrote it down in my notes, and you got it right.
Oh, I did. Oh,
Yeah,
okay.
I think so.
Okay. All right. Sorry about that. Anyway, I think the question's fine. Don't fret about the question. Oh, I know, it's right. I didn't type it in. That's the problem. I did get it right. 1 is the answer. I didn't type in the 1. That's the problem. Yeah. Thank you. Yeah. All right. Okay. So there you go. So that's what you can do too. You don't have to do the whole thing. You just do the questions you want to do, hit submit, see if you got them right or not. You do that as many times as you want. I don't care. That's a great way to study. It's a fantastic way to study. I mean, I would just go through and I just do it until I can get it right. Oh, I understand it now. Great. I'll move on to the next one. There we go. Anybody got any questions? Anything at all? Come on. You all can do this. I know you can. I know you can. I'm rooting for you. I am. All right. So what do you do? So what's your approach? You go back and we do it again. See? Now you do it again. What happens? What happens? I get a whole new set of questions. And I can do it again. Look at that. Same things though. So you didn't believe me, did you? Just numbers change. Look at that. Yeah. All right. So that's what you'll do. That's how you'll practice. Just continue to do that again and again. You'll get different answers, different numbers every time. Yeah. You know, I think, I know what some of you are going to say, but you know what? I think there's some of you out there who are going to find this just a little bit fun. Just a little bit. All right. Anybody got any questions? Anything at all? Now's the time.
I don't have a question on this because I understand that really well.
Okay.
Just for next class, because I know you showed some slides in the beginning as like a overview, like background information.
Mm-hmm.
Did we just pick up where we stopped on those slides, like for the next class, or?
Yes. Yeah, that would be fine.
Okay.
Yeah.
Thank you.
It's usually going to be pretty obvious what we're doing because, well, if you watch the videos, you'll see what slides pertain to that as well because I use the slides in the videos too.
Right. Okay. Thank you.
Okay. Any other questions? Okay, well, we'll leave it there. If anybody wants to hang around a little bit and ask me anything, they can. I will, I'll wait. I'm usually trying to be the last person to leave unless somebody's left the screen and they're not around, but anyway. Anyway, thank you. And
Hey, thank you.
see you all next Tuesday, hey?
Bye.
Bye. Have a good weekend.
Bye. Thank you.
I actually have one question.
Yes, Jack.
All right. For rates, it's bigger over smaller, right?
Yes, you try and make it that way, yes.
Is there a specific reason why that should be?
Well, it's just that if you do it the other way around, you'll end up with a fraction.
Mm-hmm.
And you'll have to find the power of a fraction. Usually it's easier to do it with whole numbers or something in the whole number range.
All right, but technically it doesn't matter.
It won't matter, no.
All right.
No, especially if you're using logs to solve it.
Mm-hmm.
It just you might be able to eyeball it and figure it out, and that might be helpful. But if it's harder if it's a fraction.
All right. Thank you very much.
Okay, no worries, Jack.
That's all I have. Everything is pretty straightforward for me. I wrote everything down in my notes, so I'm good.
All right, excellent. Okay, you let me know if you have any other questions.
I don't have any more questions. That was all.
Okay. All
Thank
right.
you very much.
Talk to you later.
Mhm.